You see massive problems on the news every day, things like clean water shortages or global warming. It's easy to look at a challenge that big and just feel overwhelmed, like trying to untangle a giant, impossible knot. But that's where the mindset of an engineer comes in. Engineers don't tackle the whole knot at once. They have a secret process. They break that huge, tangled mess into a series of smaller, more manageable strings. Our goal in this unit is to learn how to think like that, to take a complex problem and develop a successful solution piece by piece. The core idea behind this standard is all about that breakdown. It recognizes that a complex problem isn't a single thing. It's a collection of smaller problems all interacting with each other. Think of it like building a huge Lego castle. You don't just start randomly placing blocks. You build the drawbridge, then the tower, then the outer wall. Each is a subproblem. When you have successful solutions for each of those smaller parts, you simply connect them, and suddenly you have the solution to your complex castle building challenge. It's a systematic approach to what seems impossible. The first crucial step is simply understanding the challenge. What exactly is the problem? A complex real-world problem is one that is messy because it involves people, systems, and multiple factors. For example, why is traffic so bad? It's not just one cause. It's the number of cars, the road design, poor public transit, and even people's habits. If you don't research all those angles, scientific, social, and economic, you'll end up solving the wrong thing. You need to gather enough information so that you can draw a clear map of all the factors involved. When defining your complex problem, you have to set boundaries. Imagine you're trying to solve the problem of waste management at your school. Does your solution include the city's entire recycling plant? Probably not. The system boundary is your school grounds, the janitorial staff, and the students. If you don't clearly state that boundary, your project could explode into a million different directions, and you'll never finish. Setting boundaries is like creating a fence around your project. It keeps all the relevant parts in and the unnecessary distractions out. Now, for the crucial strategy, the sub-problem. If your big problem is global water scarcity, that's too vague to start designing. Instead, you isolate a sub-problem. How can we design a cost-effective system to desalinate water for a small coastal town? See the difference? It's specific, contained, and you can actually design a product or a process for it. By focusing all your engineering power on that small solvable piece, you create a building block. Once you have a few of these successful sub-problem solutions, you can assemble them to tackle the original major challenge. Let's use the example of an urban food desert. The big problem is that residents can't get fresh, healthy food. If we break that down, we find smaller, solvable challenges. One sub-problem is the expense of bringing food in from distant farms. An engineering solution might be a localized vertical farm powered by solar energy. Another sub-problem is the lack of open land. The solution could be designing a modular, stackable garden system for rooftops. Each sub-problem has its own focused solution, and together they address the larger issue of the food desert. Before you even start designing, you need to know what success looks like. These are your criteria. Think of criteria as the scorecard for your solution. If you're designing a new type of water filter, one criterion might be filter must remove 99% of bacteria. Another is filter must produce 10 liters of clean water per hour. Notice how specific those numbers are? Criteria need to be quantifiable so you can measure your prototype and know for sure if it passed or failed. If criteria are your goals, constraints are the rules of the game, the restrictions you have to work within. No engineering project has unlimited money or time. Your constraints might include a maximum budget of $500, a deadline of 4 weeks, or only being allowed to use recycled materials. You might also have legal or ethical constraints, like making sure your design doesn't harm the environment or violate any safety codes. A good engineer designs a brilliant solution while strictly respecting all the constraints. The reality of engineering is that you usually can't satisfy every single criterion perfectly. This is where you encounter trade-offs. Imagine you're designing a new phone case. You want it to be super strong, a criterion, but also very cheap to manufacture, another criterion. A heavy metal case is strong but expensive. A thin plastic case is cheap but fragile. The trade-off is the decision. Do we sacrifice a little bit of strength for a lower cost? Or do we accept a higher cost for maximum durability? You're giving up one thing to get more of another. Because of trade-offs, you need to prioritize your criteria. Which goals are essential and which are merely desirable? When NASA designed the Apollo space capsules, the criteria for human safety and reliability were prioritized far above cost or aesthetics. Nobody cared if the capsule was pretty. They cared if the astronauts would survive the trip. Prioritization forces you to make tough but necessary decisions, clearly ranking your criteria so you know exactly which one wins when a trade-off is needed. Once your criteria and constraints are set for a subproblem, it's time to generate potential solutions. This is the brainstorming phase, but it's not just random guessing. Every idea you come up with has to be rooted in solid scientific knowledge. If your subproblem is creating a self-driving navigation system for wheelchairs, one solution might involve ultrasonic sensors, and another might use computer vision. You explore all these different avenues before you commit to one specific design. Engineering is basically applied science. You can't design a better bridge without understanding the physics of forces and materials science. You can't design a better battery without knowing chemistry and thermodynamics. Every design choice is an application of a scientific principle. When you select a material for a part, you must have evidence from materials science to back up that choice. Ensuring your solution is not just an idea, but a functional, evidence-based product. In addition to established scientific knowledge, your design needs to be supported by student-generated evidence. This means using your own preliminary research and data to inform the solution. Did you run a small experiment to see which type of adhesive held up best in moisture? Did you survey potential users about the most important feature? This data that you collect becomes a critical part of the evidence base, showing that your design choices are validated by real-world testing, however small. Before you spend a lot of time and money building a full prototype, you should try to build a model and run a simulation. A model could be a physical scale representation, like a miniature wind tunnel, or it could be a computer program. A simulation is using that model to predict how the design will perform under different conditions. This is where engineers find major flaws early on, like realizing their proposed bridge design might collapse in a high wind, allowing them to fix it cheaply on the screen instead of catastrophically in real life. Mathematical and computational thinking is essential for both modeling and optimization. You'll use math to calculate things like the load-bearing capacity of a structure, the efficiency of a motor, or the total cost of production. Even simple tools like a spreadsheet can become powerful computational engines for organizing data, running cost-benefit analysis, and predicting if your solution will meet those quantifiable criteria you set at the beginning. The moment of truth arrives when you build your prototype and start testing. Testing must be systematic. You don't just see if it works. You design tests specifically to check against your criteria. For that water filter, you would run 100 liters of dirty water through it and measure how many liters per hour it produces and the contaminant level in the filtered water. You need to collect hard, quantitative data, numbers, to prove your design is meeting its goals. Once the test is over, the real work of analysis begins. You take your data and compare it directly to your criteria. Did you get 10 liters per hour? Did you only get 8? If you failed, you need to figure out why. Was it a systematic error in the design, like a leaky valve, or was it an unexpected material failure? This analysis is what turns testing into learning, pointing you directly toward the weakest parts of your solution. In the world of engineering, failure is just feedback. It's part of the iteration process. If your test results show your design didn't meet a criterion, you don't quit. You go into a loop, redesign, rebuild, and retest. Iteration is the continuous cycle of refinement. Every time you go through the loop, you get closer to optimization, which means finding the best possible solution that satisfies all your prioritized criteria and constraints. Remember, you started with a large, complex problem. You've now successfully solved one of its smaller subproblems. It's important to zoom out again and reevaluate the big picture. How does your new, successful sub-solution interact with the other parts of the system? Did that new urban rooftop garden, while solving the food access subproblem, inadvertently create a new issue, like a water drainage problem for the building? Engineers always look for these secondary, often unintended, consequences. What you've learned is the full engineering design process required to tackle massive real-world challenges. It all starts with the courage to break a giant problem into smaller, bite-sized pieces. Whether it's designing cleaner energy sources, more accessible transportation, or more resilient infrastructure, the ability to define, break down, and systematically solve subproblems is the most powerful skill an engineer can possess. This process is how your creative ideas can translate into solutions that truly have a positive impact on the world.